Can everyone hear me? Yes, okay. So in recent years, we've seen the rise of foundation models, massive ML models trained on massive data sets that generalize to a variety of different downstream tasks, right? Often these tasks go beyond the tasks that we're seeing at training time, and sometimes we call that emergent behavior. So sometimes we see that when we scale up our models, these models pick up the ability to understand jokes, to write poetry, even to engage in logical reasoning, and so on. And of course, when we think about foundation models, we think about LLMs. Here's a outline, or here's a timeline, I guess you could say, of some popular LLMs to have been released in recent years. It's a little bit outdated, but kind of the key thing is, I use my laser pointer, is this inflection point here, our ChatGPT moment, right? This is the moment when LLMs were launched into the public consciousness for the first time. And so today, LLMs are maturing, they're stabilizing, to the point that if you were to go to any of these different LLMs along this timeline, you would see very similar architectures, very similar models, very similar training recipes, and so on. So for today, I'd like us to think about LLM training infrastructure as having stabilized in the future as a black box technology, okay? And so emphasis on the training infrastructure. I actually think that inference is something that everyone uses every day. They don't even think about it, so of course that's technology to them. But training infrastructure will, likewise become black box technology in kind of in the compiler sense, if you think about it. So when I write a C++ program, I know what I'm doing. I know what program I'm trying to write, and then I click compile, and then I stop understanding what happens, right? So I have no idea what's going on inside my compiler, but then at the end, it hands me back something, and it's going to work. And likewise, LLM training will play that role. People will use this. They won't understand what a transformer is. They won't understand what is the definition of an attention mechanism. It'll just work. And the analogy goes a little bit farther than that. So compilers are a way for us to convert our specification of a program in code to that program. And LLM training will be our way of converting our specification of a program, not using code, but using input-output sequence pairs, right? And so there's that side of the analogy too. And so anyway, today I'm going to be talking about two vignettes, kind of two stories of us using LLMs in this way without necessarily digging into the innards of the LLM, but using them as this black box technology. Story number one will be video generation from my work at Google. And story number two will be robotics from my current job at Scaled Foundations. And in both of these examples, we're using LLMs as this black box technology and following this. You can sort of think of it as a three-step procedure where we're mapping our inputs and outputs to a special language in some way, and then we're setting up this almost language translation task. And that's the work that's required. Then we press go on an LLM training sort of off-the-shelf implementation, and it just works. Okay, so the first paper is kind of along these lines is VideoPoet, a large language model for zero-shot video generation. This is joint work with a large number of collaborators at Google, so I'd like to thank them. Let's think about the last 10 years or so of video generation. So we've come a long way since our kind of early days of GAN-based pixel-level methods. So here are some examples from 2016. Today, people have scaled up their models. They're using slightly better methods. They're using a lot more data and getting results like this. And in fact, if you look at some of the most recent state-of-the-art video generation models, some are listed here. This is not an exhaustive list by any means. You'll notice that they're all based on diffusion. latent diffusion, okay? And so the question that we were trying to solve when we started this VideoPoet project is latent diffusion the only way to generate nice videos, high quality videos, right? And the reason why that seems like it should be weird is if you think about the field of generative AI, we have this weird, suddenly strange branching. So if you want to generate high quality text, you need to use LLMs. And if you want to generate high quality media, images, video, audio, you need to use diffusion. So why should that split be? Why can't we just generate videos using LLMs, for example? Or vice versa, why can't we generate text using diffusion? So anyway, today I'm going to talk about that first kind of why, which is, why can't we generate high quality videos using LLMs? And the answer is, well, we actually can, and we're going to use VideoPoet to do that. So let me introduce you to the VideoPoet model. So VideoPoet is a multimodal foundation model. It takes multiple modalities of possible inputs. So you can give it a text prompt, you can give it an image prompt, you can give it multiple different types of conditioning signals, such as depth or optical flow. You can give it a mass video. And VideoPoet will take that input and it can do multiple tasks on top of these possible inputs, such as text to video, image to video, video stylization, video in-painting and out-painting, video to audio. This is not an exhaustive list, so the list actually goes on. And on top of that, no diffusion anywhere. So VideoPoet is based on an autoregressive LLM all the way through and still manages to get high quality video generation results. So I'll tell you about how we do that. First, what we have to do is take these tasks that I just told you about, image to video, text to video, and so on, and we need to convert them to a sequence-to-sequence problem. The way that's going to happen is here's our sequence of tokens that you can imagine our VideoPoet LLM, it's going to be an off-the-shelf LLM, is going to operate on. There's going to be an input part of the sequence. That's going to be the prompt. And this prompt needs to capture a instantiation of a task that the user would like VideoPoet to do. So for example, we might tell VideoPoet, hey, I want you to generate a to execute a text to video task. The text will be elephant riding on a bicycle, wearing a purple hat, and I want you to generate 2 seconds worth of video at landscape aspect ratio. So that's the kind of specific thing that we might tell VideoPoet to do. That information needs to be squeezed into a 1D string of discrete tokens. That's going to be our input sequence. VideoPoet will run its LLM, same as ChatGPT style, and give us an output sequence. A little bit more detail. So task tokens are here. It's a little bit small, sorry. So it's task tokens are a discrete token. They tell you can choose between a few options. There's like, text to video, image to video, video to audio, and so on. Similarly, on the other side, we have the so-called control tokens. There is where you specify to VideoPoet the number of seconds to generate for the aspect ratio at which to generate video. We have our text tokens here in the middle. So text tokens capture your text prompt. So here we have an astronaut starts dancing on Mars, colorful fireworks then explode in the background. So the next thing is the most interesting thing, which is the visual tokens. So visual tokens happen on the input and the output. On the input, we might want to condition on an image or video. So it could be like this Mona Lisa image, and we might want to animate that Mona Lisa image, right? So what we're going to do is we're going to use an off-the-shelf visual encoder, which takes the input image or the video and computes a 1D set of discrete tokens to represent that image or video. I'll tell you more about MagViv v2 in a bit. But what happens is that becomes a sequence of discrete tokens, and then on the output, we also output the sequence of discrete tokens, and we use a decoder, off-the-shelf decoder, to convert that back to RGB pixels. We choose to use the MagVit V2 video tokenizer, which is a quantized VAE, or variational autoencoder. And the one, I would say, key design decision here. There are a lot of design decisions in MagVit V2, but the one that was important for this paper is the temporal causality of it. So this is using a temporally causal 3D convnet, and that is the thing that lets us train jointly on images, short videos, longer videos, and so on. And that's beneficial because there are a lot of text annotated images and not as many text annotated videos. And so that lets us train effectively on a much larger data set than would have been available to us. Video is very rich. So in order to capture that with discrete tokens, you have to use a lot of tokens, a very large vocabulary. We end up using 2 to the 18th. So you can think of that as 260,000 possible visual words in the vocabulary. And that turns out to help quite a bit for quality. Similarly, we use an off-the-shelf, what's called sound stream encoder and decoder to take audio inputs and to output audio outputs. So similarly to MagVit V2, SoundStream is a quantized VAE, and it uses a causal convolutional neural network, this time 1D instead of 3D. Okay, and that's everything. That's how VideoPoet works. We've converted everything to this language of tokens, and now what we can do is we can press train on an off-the-shelf LLM implementation, and it'll just work. I'll show you results soon. But it's worth thinking a little bit about, the why of all this, right? So it's conceptually nice, conceptually kind of satisfying that we can train video generation using an LLM, but why would we do this? Here's a few reasons. So one is it's really flexible to use the system. You can kind of come up with new prompts, new ways of conditioning the model, and that's pretty easy to just insert into this new language. The other big thing is efficiency. So with diffusion models, you often have to run your diffusion model many, many times in order to get a good result, right? It's not uncommon to have to run the base diffusion model 50 times or more to get a good result. Here with the LLM, we run it once, and that's it, and we're done. So it's a lot faster. A little bit about the training data. Like all good foundation models, it's trained on a large amount of video data. It's a mixture of pre-training data sets. I won't go into the details, but we have kind of one of the big data sources has video and audio. One of the data sources has video annotated by text. We also have a large image and text annotated data set. And so that combination all gets thrown into the mix. And then finally, at the end, we have a post-training phase where we fine-tune on just the video-to-text data set that happens to also have very high-quality videos, and that helps boost the quality of the videos and the textual adherence of the prompt following, right? So that's the training data side. We also include a number of different tasks that VideoPoet is forced to do at training time. Kind of the basic one is this unconditional task where just you give it nothing and you ask VideoPoet to produce a sequence of video tokens or a sequence of audio tokens. We also have a continuation family of tasks where you give it part of the video and then you ask VideoPoet to continue the video, or you give it part of the video and audio and you ask it to continue that. We also have cross-modal tasks where we give VideoPoet video and ask it to predict audio, or we give it audio and ask it to predict video. And finally, we have these text-based tasks where we give it text and ask it to predict video, and various combinations kind of thereof. So I'm going to mostly skip this slide. We also have a super resolution module in the paper. You can check it out if you want. That takes the a smaller video and up-resolves it to be somewhat higher quality. But here are some of the text-to-video results from VideoPoet. And I'd like to just highlight some of the high motion quality that we can produce, even though this is all using discrete tokens all the way through. To highlight some of the examples here, here we have a vaporware fashion dog in Miami, looks around and barks, digital art. A large blob of exploding, splashing rainbow paint with an apple emerging, 8K. And a family of raccoons living in a small cabin, tilt shift, arc shot. Okay, we can also do image to video. So here we're giving VideoPoet a single image as well as a text prompt. A ship navigating the rough seas, thunderstorm and lightning, and it's going to be able to animate that based on the image and the text prompt. We have a 3D rotating camera ability too, so we can give it an image and ask VideoPoet to generate a fly around of the object, and that seems to work. We also support video stylization and video editing. Okay, here are some fun video to audio examples. I think I won't play all of them, just a few. So here, by the way, we are generating video based on text prompts and then asking VideoPoet to generate the audio stream that accompanies that video. Oops, let me try that again. That's a dragon. I know it's a little bit dark. Okay. I won't go into details. We compare VideoPoet against some of the competing methods. VideoPoet came out early 2024, early this year. So we're comparing here against models that came out early this year. And at that time, it was outperforming. I'd be happy to have a discussion about kind of where this stands against the current state-of-the-art offline, if anyone is interested in that. But I'd like to put it all together. So here is a slightly longer video created by some of our collaborators at Google. The way this works is it's using an LLM to generate a script for video, and then using that script, the LLM then to generate prompts for VideoPoet, and then using VideoPoet to generate the video itself.
In the Amazon raccoon forest lives Rookie the raccoon and his family. Rookie loves to play soccer with his friends, collect acorns from the trees, swim in the river, and catch fish. But what he loves most is exploring new places and sniffing new smells. Except he's never made it out of the vast forest. Every night he dreams of seeing exotic places like Times Square and the Golden Gate Bridge. One day he sees a portal of yellow light, and his curiosity makes him step inside. Suddenly he's falling through a long tunnel which takes him to Paris. I've never seen anything like it, he says. And then to the Great Barrier Reef and even the South Pole, where he makes some new friends, before visiting the ISS and ultimately the planet Androida, where the locals didn't speak raccoon, which makes him miss the raccoon forest, and especially his family. Rookie quickly finds his way back home. He's so happy to be back with his friends, but also grateful for his adventures. I guess he's not such a rookie anymore.
Okay. That's VideoPoet. Just to summarize a little bit, the takeaway should be if you want to do video generation, there are a lot of great diffusion models out there, but know that that's not the only way. All right, so VideoPoet is able to get very strong results for video generation, and I feel that this is a good way for us to challenge this diffusion monopoly that exists out there. So, if I may, I'd like to put VideoPoet in context of all the exciting AI work that's kind of come out in recent years. So here's that LLM rocket ship, this inflection point, right, the ChatGPT moment. And if we think about image and video generation, I would say that it's followed a somewhat slower but maybe similar trend, right? So early on we had DALL-E and Imagen. At some point, stable diffusion came out and really it made this technology quite widespread. And today, we have really strong video generation solutions available to us. Sora, Runway, Luma, and so on. And of course, VideoPoet falls somewhere along this trajectory. But I think the exciting thing to think about really is what's next for AI, right? What's next? What's this next rocket ship, or what's the next ChatGPT moment going to look like for AI? And one modest proposal from me is that I think the next ChatGPT moment might just be robotics. So I want to talk a little bit about that. So robotics is hard. It's really hard because of two main things. So first you have to get the software right, and then you have to get the hardware right? And every robot has its own hardware stack. You might have a hard time coming up with truly generalizable solutions in robotics today. And so that's a big challenge, but every robot has to do basically three things. So one is to sense the world. One is to make a plan of how to act, kind of based on the sensor measurements that it got. And then thirdly, it needs to act, of course. So now traditionally, roboticists had to come up with three separate approaches. They would design kind of separate modules for each of these three pillars of robotic AI. But today, things are changing. So there's been a big shift in recent years due to deep learning, of course. So now there are deep learning solutions for perception, planning, and control. There are exciting methods that put all three of these things together and train end-to-end. And the other thing is cloud computing. So with the rise of AWS, Azure, GCP, we now have the ability to, of course, train on large data sets, but I think particularly for robotics, we have the ability to do robotic simulations at a much larger scale than previously possible. So for these reasons, earlier this year, I left my post at Google Research and kind of went to a small company also in Seattle called Scaled Foundations. And so I would like to say a little bit about what we're doing at Scaled Foundations. So here's the traditional robotics pipeline. This is a musher robot. It has a LiDAR on the top. It has a few sensors. It has, cameras, RGB cameras, stereo cameras, and an IMU. And with these sensors, it has to solve several tasks. It has to do mapping and localization. It has to do motion planning. It has to execute on that plan using the low-level steering control that it has access to. And kind of traditionally, going back, traditionally these three things work separately, right? So traditional roboticists would do separate modules for each of these things. And that works okay. So here's an example of this musher robot going around in an indoor office environment using traditional motion planning. And it may not be that generalizable or anything, but for kind of this purpose, it's doing all right. But of course, in our future, if we're looking towards the future and we're thinking about what will it look like in this post-robotics ChatGPT moment world, of course, what we like to really do is replace those three squares by this single model called, single foundation model. And that single foundation model will be trained on lots of data. It will hopefully ingest multiple modalities of inputs. Maybe it takes LiDAR, and it takes camera images, and it takes IMU, right? And like VideoPoet, hopefully it'll be able to do multiple tasks, such as mapping localization, motion planning, and controls. And hopefully it's been trained on so much data that it's able to react to any given situation that it can come across, okay? And so I'm not going to claim that we've kind of landed all the way there yet, but I'd like to give kind of talk about a small step towards this dream of foundation models for robotics. This is a project that people in Scaled Foundations are working on called PACT. So PACT stands for Perception, Action, Causal Transformer. Like GPT-3, like any LLM, or even like VideoPoet, PACT is taking a sequence of input tokens and converting it into a sequence of output tokens. Like VideoPoet, it's taking, it can take multiple modalities of inputs. So you can imagine giving PACT images, a depth image. You can imagine giving it LiDAR, or maybe you want to tell it to go fast or go to the kitchen, right? And instead of outputting language tokens or video or audio tokens, PACT is producing actions. It's going to predict a bunch of actions for the Musha robot to do. The Musha robot will take an action. Maybe it lands in a new state in its environment, and then we get new sensor inputs, and we close the loop like that. Okay? Like ChatGPT and VideoPoet, we're building on top of a off-the-shelf decoder-only LLM, decoder-only transformer model, and pre-training this on a large amount of robot trajectories. And once that's pre-trained, we can fine-tune PACT on a variety of different downstream tasks. Could be new tasks, could be new environments, it could be new input modalities, okay? And so just to give a small kind of sample of, or a small demo of what this looks like, here we have our Musha car driving around. It's been fine-tuned on a new indoor environment. And instead of using classical approaches to robotics, what it's doing is it's taking its LiDAR, it's taking its images, it's feeding it to PACT, and just getting this prediction of where to go next. That's visualized by this red arrow here. Okay, so you can see it driving around in its environment. So that's great. This only works for PACT. It's been kind of, you can imagine it's been overfitted to PACT. But wouldn't it be amazing if we could get something like this, right? PACT-like foundation model behavior on any generic robot available, okay? And yes, of course it would be amazing, but this is really difficult today, and it's difficult for two main reasons. So one is there's a scarcity of expertise in the world. By one measure, for every 20 AI engineers out there, only one of those has real-world robotics expertise. Problem number two is that there's a lack of data sources for robotics. So that's true for many, many reasons, but one data point to show this is that if you were to go on Hugging Face, you would find over 100,000 data sets or data sources to download, data sets with which to train your generic AI models. Of those, only a tiny sliver, right? Less than 100 data sets are what you could properly call a robotics data set. So you can imagine today that if you want to train an AI model, you can download MNIST or ImageNet or MS Coco and type a few commands, and you'd be training within hours. The pipeline is sort of quite streamlined these days, but that same workflow kind of getting your feet wet doesn't currently exist for robotics. So that's the problem that we are trying to solve at Scaled Foundations. And what I'd like to do is tell you a little bit about our new development platform called GRID. GRID is GRID here and stands for General Robot Intelligence Development Platform. On GRID, when you write your robot code, you can deploy it in simulation. You can deploy it on a real robot. You can use GRID to generate and collect data. You can use GRID to train on that data set and deploy that model, again, in simulation or real world. And then you can use GRID to monitor what the robot's doing while it's operating. So just to be a little bit more concrete about this, if you have an idea for for what you'd like to implement on your robot, then you can write it in Grid. It might be in this Colab notebook environment that we support. And when you do that, you have instant access to API calls to a number of different robot form factors and a number of different AI foundation models that are already available out there. Okay, so things like Clip or SAM2, these are things that you could just call directly from inside Grid. When you press run, you can see your robot running immediately in the simulation window. You don't have to wait a long time to put it on a robot, and possibly have your robot break. You can just see it running in simulation instantaneously. Of course, when you're happy with your code in simulation, then you can push it onto your robot and see it work there. So we hope that this will significantly speed up the development of robots. That's why we like to think of Grid as every robot's AI engineering team, right? We support a number of different simulation possibilities. You can put your robot indoors, outdoors. You can even put your robot on the moon or Mars in Grid, simulation, of course. Here we are kind of modifying textures, modifying objects, bringing in different meshes from different sources. You can customize the environment to be different times of day. Here we go. Here we are flying a drone through rain, through adverse weather conditions. That's the kind of thing that's supported. We can support externally scanned environments. That's Seattle. Like I said, with Grid, you have access to AI models that you can use directly in your code. But if you don't want to write code on one particular day, you can just talk to Grid. You can just talk to your robot. So here we are talking to Grid. The user says, "What do you see?" And Grid says, "There's a forest with trees and a large fire burning," and so on. And then, oops. Then the user says, "Find a safe vantage point and fly there." And Grid complies. Okay, I'll skip that one. Okay, I'd like to put it all together and show what this looks like when we use the code we've written on Grid and put it on a real robot. So here, we're asking Grid to do this high-level task. Grid then decomposes it into lower-level subtasks, and then we're asking the robot to execute on each of those lower-level subtasks. Okay, thank you very much. I'd like to thank my collaborators, both on VideoPoet and on Pact and Grid. I'd like to thank the Scaled Foundations team. And if anyone's interested in Grid, if you're academic, there's a license there that you can get. Otherwise, you can just contact me directly, and I'm happy to connect you. Thank you.
Thank you, Jonathan, for the great talk. We'd like to take some questions, one or two. If you have any, please raise your hand. So can you pass the microphone?
Thank you very much for the interesting talk. I have two questions, one for the first part and the other for the second part. So first question is, you said video generation is usually done with the diffusion models, but why not with the LLM? And it kind of worked great. But in my understanding, so text is like purely discrete, right? While videos are very like continuous, well, sampled from continuous world. So there is a very different features within these modalities. So diffusion model is probably very well to represent this kind of continuous world, while LLM is good at controlling the discrete modalities. So I was wondering why why LLM worked like greatly and could beat diffusion models. So I want to ask your opinions why it went well. The second question is, it's of course it's great if you can build a foundation models and do everything, but it's not very efficient, right? Our brain is not made like that. We have like each modules, and each part has their own roles for perceptions or with linguistic processing, whatever. So yeah, I also want to ask for the second part. Do you really believe that only one foundation model is enough? Or yeah, I would like to ask what is your prediction for the future direction? Yeah, thank you.
Okay, thank you for the questions. Okay, so the first question is about the fact that we're modeling continuous data with an LLM, which seems unnatural in some ways, right? I would say that if you were to poll the people on my team of collaborators that work on this, not everyone believes that LLMs are totally suitable to this task. And I also really like diffusion models. I'm not saying people shouldn't use diffusion models. So my answer though is, first of all, I mean, of course we represent our images, our video, all digitally. So in some sense, we're always representing things in discrete ways. I think that's one kind of way to think about it. The other thing that is very important here, that I think I swept the difficulty under the rug, is the design of the tokenizer. I said that we use an off-the-shelf tokenizer for the videos, which is true in some sense, but the truth is people have worked very, very, very hard to get a high-quality video tokenizer that does vector quantization, that gives you really, really good results. So today, when you look at kind of the results for VideoPoet, it's hard to say that it can't do video generation. It clearly can, and I also don't see a bright line that says this is the limit and we won't get any better. I actually think that if you were to take VideoPoet, train on better data sets, and maybe train with larger resources, you could approach the quality of some of the leading video generation models circa December 2024, right? Okay, so the other question was, do I really believe in kind of single model for robotics? I do believe that. I think there are benefits to having multiple models. It's it's easy to debug, so that's kind of one good thing. But we've seen over and over this trend in the community to unify, and I think there are a lot of reasons to do that, including being able to train on larger data sets, being able to include tasks in the training mix that maybe aren't directly the thing that you're trying to do, but still are informative for the task that you're trying to do. that really helps, and it helps at really large scales. So it's always better to, my bet would be that we're not there yet, but my bet is that we're going to land in a future where things have been unified into one really, really big model.
Yeah. Thank you for the answers.